So, good morning. So, today is now lecture number 25th. So, last time we had started about, I gave you something preliminary lecture on curves, a simple curve, and then I said any point on the curve can be located by a position vector r, and then you take 2 points on that curve at a distance, with two position vectors, that is r and r plus dr, join them by a vector, so that will be dr, and dr, if you take dr divided by ds is the scalar length along the, so that happens to be, that we proved that day, that it turns out to be unit vector. Dr by ds dot dr by ds equal to unity. Dot product is unity, it is a unit vector. And not only it is a unit vector, it is also a tangent vector at the point P. Dr in the limit as ds tends to 0, it will be tangent to the curve at point P. So, this much we have done, and so this is for a curve. So, and then we went on to a surface. The surface, see, you need a net of two curves if you want to define a surface. So then I said, okay, if you have a point P here, point P in space, its location as usual can be fixed by a position vector. You fix your origin here somewhere, draw a position vector r. But now r is moving along, it is moving not along a curve, because this was a curve earlier, supposing it was a moving in curve. Now it can move also along another curve. So let us call this curve as alpha curve, this, and this one as beta. And of course, these curves are having different values of what? Constant, they will be having different value, because it is alpha, so alpha equal to this one, this curve is there. So these are different curves, beta 1, beta 2, beta 3, for different values of alpha, just like you have x1, x2, but only thing that this is curved. Now, basic point in surface is, because this is a, so now there are net of two curves, alpha and beta. Now, yes, so what will be this? If I, proceeding in the same manner as we proceeded earlier, if I take another point here Q, and join this by a surface ds, length, arc length ds, and then join this Q point by this, whose value is, now this vector is r plus dr, it is a vector. So r is, as before, I don't want to make mistake. So first of all, we define a surface. A surface in parametric form is defined in number of ways. One is that you can also define this as so a surface in parametric form and the parameters here are alpha and beta. They can be defined as x which is a function of alpha and beta, y which is a function of alpha and beta, and z which is a function. And how it is so what is a surface? So surface in a parametric form is defined as this two functions. So I can just define this mathematically. In words, how do you define this? It is a locus of points, locus of a point whose position vector of a point whose position vector R is a function of two parameters alpha and beta. Now alpha and beta, these are called curvilinear coordinates. Curvilinear coordinates. They are curved. These lines are not a straight line, not like in a and curvilinear coordinates of the surface, you can say, of the surface is also defined if you see any book on mathematics. So if you call this as equation 1 here. See, if we eliminate alpha and beta in 1 somehow, then we can write down, if we eliminate in equation 1, then we also get the common form of surface definition, and that is this. And that is some function of x, y and z equal to 0. This way also is another, if you see any book on mathematics, you will find that surface is also defined by, so one is parametric form, other one is, and of course there are usual things in mathematics that x, y and z are single valued. X means x which is a function of alpha and beta, y which is a function of alpha and beta, z which is a function of alpha and beta are single valued. They don't have multiple valued, V-A-L-U-E-D, single valued, and continuous, because not that surface we cannot define if it is discontinuous, and a continuous function of alpha and beta. So vectorially it is the tip of the R vector. I can move and I can define a surface. From O, my position vector is this, so it can move and that will be the locus of all such points will be a surface. So tip is so vectorially we define a surface also as, so there are so many definitions, that will be 3. R equal to R alpha beta, it is a function of 2 variables, and R is means xi plus yj plus zk. So this is 3. So 3 ways in which a surface can be. So R is a position vector joining any points on the, that is okay. Now what as a theory of shells, what we will be needing, because we would like to know how to measure a distance on the curved surface. What is ds, etc. What is ds between 2 points P and Q? How can we find out ds? So let us now try to make use of differential calculus. Vector algebra and vector calculus. Simple vector calculus. It is not that. So I will skip all the descriptive part. So I will just explain to you how to. Now R is there. So R, if you take a derivative of R with respect to alpha. So let us define. I define, normally a derivative is defined by a comma, R comma alpha, like this, means it is dr by d alpha. Many times this comma nowadays also is not written. Even just simply R subscript alpha is also okay. This also derivative. That means this is equal to dr by d alpha, and dr by d alpha will be nothing but dx by d alpha into I plus dy by d alpha into j. And similarly R beta, that means I am taking the derivative Now, what are R alpha and R beta? From your whatever we have learned, derivative of R with respect to alpha. Along alpha, a curve is there, parametric curve. I am taking derivative of, we have seen what is dr by ds. Dr by ds happens to be a unit vector. It turned out to be a unit vector, but it was a tangent vector. So dr by d alpha also, one thing is clear, it will be a tangent vector. So it will be tangent on alpha curve, and derivative of R with respect to beta will be a tangent on beta curve. Okay. So these are tangent. There is a lot of commotion by tangent to the alpha and beta curves. Let us say they are just tangent. I am not saying they are unit vectors, because they are parameters. They are not S. There is no alpha and beta are not, do not have the dimension of a length. They are just non-dimensional coordinates. So they will be simply tangent vector along alpha and along beta. What about this? R alpha modulus. That means its length. Let us call that as equal to A. Let call it, say. Similarly, R beta, let us call that length is B. Length of tangent vector is B. So therefore, I can write A square, it will be equal to R alpha dot R alpha, and that will be is it okay? And B square will be R beta dot R beta Now these A and B, which are the lengths of R alpha and R beta, A and B are the lengths. They are not unit vectors, they are some vectors, tangent vectors, but they are tangent vectors at point P. So these are called in surface mechanics A and B. A and B, these, the magnitude of the vectors, they are called Lame, L-A-M-E, Lame, great mathematician. So Lame parameters. In the definition of surfaces, because this will be, so they are called Lame, L-A-M-E, his name was. Now R alpha divided by its, what will be this? What will be this? This is okay, I am dividing R alpha by its magnitude. This is magnitude. A is the magnitude, so it will be what? Unit vector, unit tangent vector along alpha. So this will be now unit tangent vector. It is denoted by, in the book of Krauss, it is denoted as alpha like this. I also denote it as alpha tangent T, tangent vector along alpha. And similarly, R beta divided by B is unit vector, unit tangent vector. So tangent, so these are unit tangent vectors to alpha and beta curves on the surface. What will be this? R alpha, this means T alpha dot T beta. Tangent vectors on the surface at point P to this dot this. What will be this? simple, two unit vectors. These are unit vectors. Two unit vectors. Dot product of two unit vectors. What will be? Angle is general angle. I am not defined angle. Angle is anything. Cos of angle. Yes, cos of angle between. Let us say the angle is kappa. Angle is, so on the 2 you have, this is alpha. So this one is alpha, this is beta. So here this is T alpha, this is T beta, and this angle in between these two tangent, this is kappa. And what is this? Cross product. Cross product will be what? Sine. Just sine, no. Cross product, first of all, cross product of 2 will give you a normal vector, plane containing this. It will be a normal to the plane containing T1 and T2. So that is one, it defines the vector and multiplied by sine. Is it okay? This is alright? Vector algebra, which I have forgotten. So I can say that the normal vector, let us define it by En. En is the normal vector here. Between this and this, T alpha and T, there is a normal vector En, and that will be equal to T alpha cross T beta divided by sine kappa. So at least we have now, this is a unit vector. So this is again a unit normal vector. Vector at P. And this is at P, that means to the surface, at P to the surface, normal to the surface, yes. So now you have got a set of T alpha, silence please, T alpha, T beta and En as a set of three unit and you know the definition of what is the definition of unit vector, and of course En will be, if you form a plane containing T1 and T2, then En will be perpendicular to that. Similarly, you take the other one, T alpha and En, and if you take a cross product of that, then you will get the other vector T2. See, it is like this, 1, 2, 3. So any cross product in cyclic order, you will get the other unit vectors. So we have defined. T alpha, no.
So if I do En cross T alpha, I will not get T beta.
You will not get T beta, no. Because angle is not orthogonal. That sine cosine will come. But direction is fixed. What you will get is a direction that will be same as, if you take this and this, you will get this direction. No? Oh, sorry. You will not get. Yes, you are 100%. No, you will not get. Because they are not. I am sorry. If I made that mistake, yes. It will not be. T alpha and T beta are having a plane in it, and perpendicular to the plane is En. Yes, let us stop there only. Okay. So, all right. So, we have defined a unit, it is called triad, T-R-I-A-D, triad of unit vector. 3 unit vector, which is also called triad, T-R-I-A-D. Instead of this. So far there is no shells, there is only, but then today we must finish it. Then what should we do? There is one more. How to find out? So one thing is, now let us recapitulate. So we have got R alpha equal to A times E alpha, or A times T alpha. See, R beta, which is equal to B times and R alpha dot R beta equal to A and B cos, yes. So now we are taking P and Q. So what is saying? P, the coordinate of P is alpha beta. From here we go to Q, alpha plus delta alpha and beta plus delta beta. I want to find out dr, which we have already done earlier. So it is equal to dr by d alpha into d alpha plus dr by d beta into d beta. And since it is A and B is known now, so we can write it A into T alpha into D alpha, B into T beta into D beta. What is this? dr dot dr from vector algebra. Go back to your it is the increment length on the surface. So it is equal to ds whole square. It is a scalar and it is square of the length on the surface, ds. So ds is the distance between P and Q, curved ds. So ds square is given by dr. So therefore that is, and that if you do dr dot dr, so you are getting a square d alpha square. I will do it quickly, into cos alpha, cos kappa into d alpha d beta plus b square into this is the dot product. So this is a very important thing, because now we have got a formula which can give you an arc length on the surface. So this is called first fundamental form of the surface. In theory of surfaces, this is called first fundamental form. First fundamental there are number of adjectives added to this. It is called sometimes quadratic form, sometimes quadratic because it is quadratic, sometimes differential form, but I think I will write it simply form. So now, see, this helps us. Now we'll take a special case. Kappa equal to 90. Let the nets be orthogonal. Alpha and beta be orthogonal too, so that the angle between them be 90 degrees. Then what do you get? Then you get simply ds whole square is equal to a square d alpha square b square d beta square. The middle term, because cosine or sine, what was it? In between, cosine 90 equal to 0. Cosine 90 equal to 0. So you get a simple form. So now there are two theory of surfaces you can have. You can develop theory of shells based upon non-orthogonal coordinate system. You can also develop a simpler shell theory based upon orthogonal coordinate system. Now non-orthogonal system, we have not studied even in a plane non-orthogonal. It is called skew plates. If you want to define a 30 degree a plate which is x-axis is here, y-axis is making 60 degrees to, then and you develop a plate rectangular. It is called skew plate. You can derive all the equations of plate theory in skew coordinate. That becomes much more complex. There is a book on skew plates. Okay, so you have to take skew coordinates because this we have taken a orthogonal coordinate system, orthogonal Cartesian. So here also we will take orthogonal coordinate system because lot of mathematics will be, complications will be simplified. But then there is a one book which has been written on shells which deals with only skew coordinates. Kappa equal to not equal to 90. It is by Goldenweiser. The book is there in our library. At least see the Goldenweiser. This is book on shells when kappa is, and as you see when the name, he is from Soviet bloc. This person, it's a classic book, Goldenweiser. The idea is you can develop lot of special forms. If you take this non-orthogonal system, you will get a special forms of curved surfaces. So not only simple cylinder or a sphere, but something very funny, very complicated you can develop. So those skew will be needed for defining a complicated shell form. So there is a book, A. Goldenweiser. Okay, so this is I think this is the first fundamental form is all right, and because this will be used, for defining any surface. There is also another form which is called next part of the theory of surfaces, where we derive the second fundamental form. And second fundamental form helps us in finding out the curvature. This has helped us to find out an arc length on the surface. Second fundamental forms give you what is the radius of curvature at point P. radius of curvature or 1 by r. So that helps us to, so second fundamental form helps us define radius of curvature at P on the surface. Now, I don't want to discuss that because it is a little complicated. Honestly, it will take a number of lectures. So, as and when it comes, we will deal with it. But please try to read the first chapter of Krauss' book. First chapter, it gives you some idea about, because he has also taken it from some book, from some mathematics book, some preliminary formula, etc. he has given. So, read from Krauss' book, and that helps us to. So, this is about the general theory of cells. I don't want to take anything more. So, now we will, with this much, I think I can develop any cell form. We will be using orthogonal curvilinear coordinates.
Again, assuming x, that x-axis and y-axis are perpendicular, not that alpha and beta are perpendicular. Are we assuming that?
See, x and y are any point, we are fixing our coordinate. Alpha beta is lying on the surface. So, alpha and beta are orthogonal. Now we are saying.
Alpha and beta are
Orthogonal, we are saying. XYZ anyway is normal with reference to a fixed point O. We are defining our radius vector, which is on the surface. And now we are fixing another coordinate system on the surface, alpha and beta. Okay, so now go to the cells. There is a simple formula which tells us. See, I have tried to simplify, but then I have not. I will just try to scribble something and then see whether it makes any. See, n is the normal vector, let us say, unit vector, normal to the surface, n. Now, En, just call it n. Just this dot, the tangent to either alpha or beta, let us call that as t. This is also a unit vector. So, this, if they are orthogonal, this will be 0. Cosine 90 equal to 0. So, tangent. See, tangent on the surface and normal. Dot product is 0. So, now let us see. Now, if I take the derivative of this with respect to S, S is the arc length, ds. So, dot t plus n, I don't know whether it is. This also is 0. In general, I am saying, any t you take, any tangent vector you take, any normal vector you take. So, this is, we are just doing dn by ds into t, tangent vector, what is dt by ds? Anybody? Rate of change of tangent vector on the surface with respect to S. That is, gives you, yes, that defines the change in, that is the change in the direction, vector. So, that defines your curvature, dt by ds. And so, this dt by ds is plus, so this is okay, plus n dt by ds, you see, you are here on the surface. Let us say here tangent dt by ds next. This is S. This will be R. So it will be, I mean, you must realize that dt by ds in the case of plates will not change, is 0. In the case of plates, dt by ds, it is the same. What is difference between a plate and shell? Most important, I mean there are two parts. One is the geometry. A curved plate is a shell. Or two curved surfaces at a small distance. The area enclosed between these is small distance is called shell. Okay. So this is the basic geometrically. What is the mathematical definition of a shell? Where the normal changes its direction as you move on the surface. The normal. So difference between plate and shell is that normal in a case of plates remains the same. No change in the direction of the normal. While in a shell, as you are moving from P to Q, the direction changes. So this is the mathematical or mechanics definition of shell. So now dt by ds is the one which is changing, and that gives you what is called curvature. Let us say k times n. Because curvature also will be, curvature is scalar. This is, I am just saying curvature is scalar times, and it is in the same direction of n. This is scalar, is same in direction of n. So it is this dot n. And so kn, and this total thing is called many times by, it is also written as n dot kn vector. Kn will be, this will be vector 0, and therefore kn will be what? Minus kn will be minus dn by ds dot t. Sorry. This is scalar k. This becomes unity. So this is called kn. Sorry, this n will not come. This is called kn. Normal curvature. See this n, k, this is n, so this is dot equal to unity, and so this is a curvature. So normal, this we call it normal curvature at that point, normal curvature. So we are denoting it as normal curvature. That means in the direction of the normal. If you draw at the 2 points normal, and how do you get normal? By T1 cross T2. Normal at any point is defined by T1 cross T2. So if you do this, so then this normal curvature is given by this. And normal dn by ds, yes, so this is how he has written. This is also we can change minus T dn by ds. I think in dot product you can change the order, na? A dot B or B dot A. So this is minus dn ds. Yes, good. Any simplification? So curvature, normal curvature can be given as minus. What is tangent? Tangent vector, how do you find out? Tangent vector is dr by ds. Unit tangent vector. Yes, this we have proved. dr by ds is a unit tangent vector. So this is unit tangent vector I have taken. So this is dr by ds dot dn by ds. Or it is also written as dr dot dn. Sorry, dr dot dn. Yes, unit. And this is dot means ds square. Yes, please. So now I have given you some idea about how to find out curvature at a point. So this is a simple way of explaining. Otherwise, whatever is given in the book is little complicated. So this is, we can find out from here how to find out curvature at any point P. Okay, so this is defines curvature. By the way, just give one more explanation, which is this Kn has come out to be, see this whatever formula you get by taking dot product of dr dot dn, we call it second fundamental form. Yes, this numerator minus is called second fundamental. And what is the bottom one? What is the denominator? ds square. The formula for ds square is called the first fundamental form. Yes, that is what we have done. So divided by first. So this is all. I mean, in a nutshell, this is all. What is the definition of second fundamental form? It helps us to find out curvature at any point. And second fundamental form, if you divide, if you can take the dot product of dr by dn, that gives us second fundamental form. And divide by ds square, which is first fundamental form. So this is, in nutshell, the theory of surfaces. And this will be enough to understand the general theory of shells. And we are going to use orthogonal coordinate system. Okay. So from tomorrow there is a lecture. So I will start thin shell theory. Okay. So thank you.